Welcome back. Today on The Explainer, we're tackling a subject that is, well, it's pretty dark, but absolutely fascinating from a scientific perspective. We're looking into the world of nerve agents. Now, we're sticking strictly to the facts and data here, pulling directly from a really comprehensive study in the World Journal of Pharmaceutical and Life Sciences. We're going to methodically map out the science, the history, and the countermeasures, so by the end of this, you'll have a crystal clear picture of the whole shebang.
So here's the big question. What actually makes nerve agents the most potent, toxic synthetic compounds on the planet? It's a striking thought, right? What makes them so uniquely devastating? At their core, nerve agents are organophosphates, basically organic chemicals containing phosphorus. Now, you might know that everyday agricultural pesticides share a similar family tree, but these synthetic compounds, they are weaponized to fundamentally disrupt mammalian biology. They don't just poison you, they literally hijack your entire nervous system.
Okay, let's dive right into this. Here is our roadmap for today. We've got 5 clear parts. First, a dark history. Second, the biological mechanism. Third, the G series and V series. Fourth, detection and treatment. And finally, global bans and eradication. All right, starting with part 1, a dark history. The origins of chemical warfare. To really get the chemistry here, we first need to look at the timeline. Like, how did we actually get to this point? You know, the idea of banning chemical weapons actually predates their worst uses. Way back in 1899, the Hague Conventions already forbade dangerous gases in warfare. But well, just a few years later in 1914, during World War I, we saw the debut of tear gas, and soon after, blistering agents like mustard gas. But the true nerve agents? They didn't show up until 1938, when scientists in Nazi Germany synthesized taboon, which was the very first nerve agent. This escalation just kept going, eventually leading to the 1993 Chemical Weapons Convention, which universally outlawed their production and stockpiling. Now, during the Cold War, the US and the Soviet Union sat on massive stockpiles of these nerve agents, but thankfully, they both held back from using them. Actually, looking at modern history, Iraq is the only country to have deployed nerve agents in warfare. From 1984 to 1987, during the Iran-Iraq War, Iraqi forces used agents like Sarin and taboon, and the human cost? Staggering. We're talking anywhere from 45,000 to 100,000 casualties, with the vast majority caused by these invisible gases. Moving right along to part 2, the biological mechanism, hijacking the nervous system. Let's zoom in on the physiological level to decode exactly why the UN classifies these chemicals as weapons of mass destruction. This really illustrates the horrific efficiency of these agents. It all comes down to one single disruption. Normally, your body releases a neurotransmitter, acetylcholine, to tell your muscles, hey, contract. Once the job is done, an enzyme called acetylcholinesterase comes in, breaks down the neurotransmitter, and lets the muscle relax. Well, nerve agents completely block that specific enzyme. Because the acetylcholine can't be broken down, your muscles never get the signal to relax. They get locked in the state of constant, intense stimulation, paralyzing them. In the medical world, this is called a cholinergic crisis. Now, it gets worse because there's a secondary chemical reaction called aging. Aging is basically the process where the bond between the nerve agent and the enzyme becomes permanent. So treating this is literally a race against the clock. Imagine a countdown starting the exact millisecond of exposure. Once that enzyme organophosphate complex is aged, standard antidotes just can't regenerate the enzyme anymore. And with certain agents, like Soman for instance, this aging process happens incredibly fast. We're talking a treatment window of just a few minutes. So the crucial point here is that because this mechanism causes paralysis all over the body, and yeah, that includes the heart and the diaphragm muscles you use to breathe, the symptoms are incredibly rapid and, frankly, terrifying. Within 30 seconds of exposure, a victim will get a runny nose, a super tight chest, and their pupils will constrict down to pinpoints. This escalates really fast into a total loss of bodily function control, violent muscle jerks, and seizures. Ultimately, the cause of death is complete respiratory depression. Basically, the victim just cannot breathe. Which brings us to part 3. G series and V series, categorizing the threat. Scientists basically split these lethal compounds into 2 main families based on their physical traits. If we look at the complex molecular structures here, we've got the G series on the left and the V series on the right. Now, while they both share that deadly organophosphate backbone that triggers the cholinergic crisis we just talked about, their physical forms are very different, which means their real-world hazards are totally different too. Now, what's really interesting here is the stark contrast in how these weapons are actually used. The G series, named because they were first synthesized by German scientists, includes things like sarin and soman. These are non-persistent. That means they are highly volatile, they evaporate into a gas super quickly, creating a massive respiratory hazard. But the V series, invented in the UK in the 1950s, agents like VX are persistent. They literally have the consistency of motor oil. They don't evaporate. Instead, they're designed to stick around, blanketing the terrain and posing a lethal skin contact hazard for a really long time. All right, part 4, detection and treatment, countering the crisis. So faced with invisible gases and toxic oils, how do we actually fight back? The scary thing about agents like sarin is that they are totally colorless and often completely odorless. You simply can't rely on human senses here. By the time you feel anything, it's way too late. So detection relies on some incredibly sophisticated tech. Scientists use things like laser photoacoustic spectroscopy and various infrared techniques, like Fourier transform infrared spectroscopy. Basically, these instruments analyze how air samples absorb specific wavelengths of light or infrared energy. This lets them spot the unique chemical fingerprints of nerve gases in the air long before anyone walks into a contaminated zone. But what if exposure does happen? Well, rapid decontamination is step 1, lots of soap and water. Then comes the medical intervention, which is a two-pronged attack. First, you have atropine. It's an anticholinergic, meaning it blocks the receptors from getting overstimulated by all that acetylcholine buildup, which manages the symptoms. The second drug is 2-PAM chloride. This one goes after the root cause, attempting to physically cleave the nerve agent right off the enzyme to restore its function. But remember that aging process we discussed? Yeah, 2-PAM absolutely has to be given before aging completes, or it simply won't work. Now, out on a battlefield, nobody has time to carefully set up an IV drip. That's why these antidotes are packaged into spring-loaded auto-injectors, kind of like the Mark I kits we see used today. One syringe holds the atropine, the other holds the 2-PAM chloride. They are literally designed to be jammed straight through a soldier's clothing for immediate delivery into the muscle. It's all about buying the victim precious time. And that brings us to our final section, Part 5, Global Bans and Eradication, the Path to Zero. Let's look at the modern diplomatic push to get rid of these chemicals once and for all. As you can see from this quote, the international community fully recognized the indiscriminate horror of these weapons. Under UN Resolution 687, they were officially classified as weapons of mass destruction. And the Chemical Weapons Convention of 1993 drew a hard line, mandating a total ban on their production and stockpiling. The countries that signed didn't just agree to stop making them, they agreed to actively destroy the arsenals they already had. Let's move on and see how this builds, because getting rid of these weapons is a massive chemical challenge in itself. You can't just take a barrel of VX and toss it into a bonfire. If you do that, you just send deadly, toxic clouds floating into the atmosphere. No way. They have to be chemically neutralized or destroyed in highly specialized, closed-system facilities. It is a painstakingly slow, methodical, and crazy expensive process. In fact, it's so difficult that initial 10-year destruction deadlines had to be extended by nations like the US and Russia. So, what does this all mean for us today? That brings us to one final, thought-provoking question. We've mapped out the mechanisms, the history, and the eradication efforts, but the underlying chemistry, the actual knowledge of how to manipulate these organophosphates, is still out there. It's totally accessible. So how does the global community guarantee that these devastating agents stay locked away as a dark chapter of the past and don't become a shadowy threat for our future? It really highlights just how fragile international treaties can be and why continuous, rigorous scientific monitoring is absolutely crucial. Thank you so much for joining me for this explainer today. Keep learning, stay curious, and I'll catch you in the next one.